Okay, so let's go ahead and start the second to last session. And this is on dark matter and cosmic microwave background. And for me, it's a pleasure to be here in this KahnFest. I've known Steve for many years and made dramatic difference here at Stanford and at SLAC. In fact, the SLAC effort in the CDMS experiment comes from Steve's early insistence that it would be a good thing for SLAC to do. So I'm very pleased with that. The speakers today, Tom Schutt was a graduate student on CDMS with Bernard Sadoulet in Berkeley, so that's a very close tie. And Adrian Lee, who is on the way and hopefully will arrive on time, was my graduate student on CDMS, so that there's lots of connections. So Tom, please proceed on Lux, LZ, and the approach to the neutrino floor for dark matter.
Thanks, Blas, and it's nice to be here. I have just, as Blas mentioned, I have just a minor connection to Steve. I was a grad student at Berkeley when he was there, but there's one other connection I'm going to bring in about my third to last slide. I'm going to jump right into the story of, I'm going to take it as written that there's the dark matter, but I want to go over what should be familiar to people, the freeze-out argument for why the dark matter might be weakly interacting massive particles. I think it's worth going through. The freeze-out argument is this compelling notion that at an early time in the universe during the Big Bang, whatever could be created was created. That is to say, if the thermal energy is large compared to the rest mass of a particle, you would create that particle and its antiparticle in abundance. In fact, there'd be a blackbody spectrum of those particles. So essentially, proton, antiproton, things like that, the more heavy particles that are short-lived that we know about in the standard model. All of those would have been in equilibrium just as long as they have some sort of coupling to normal matter. And the dark matter problem is so profound that it is useful just to think about, well, what do we know about, what is possible given the idea that the particle, some sort of new matter coupled to ordinary matter. So this is just sort of a very generic idea that let's think about some sort of matter in the early universe that had a connection to, say, electrons and positrons. And then the fact is that when things cool down, at some point, you no longer have enough kinetic energy in these things to create some exotic heavy particle, but the back reaction happens and these things will annihilate away. So here, if we look at a co-moving density, this is a famous plot. Time is going to the right, or temperature dropping as you go to the right. And these things are sort of a blackbody spectrum up here, and then they're exponentially suppressed. So it's a simple Boltzmann term, e to the minus energy over kT, and energy is mc squared. And so as you drop off, these things are gone. There's no thermal sea of antiprotons today. But there's an escape clause. This back reaction of annihilation has to happen, and that's a cross-section times the velocity times the number density. And if that amounts to a rate, if that's equal to the expansion at the time, then these things, they never find each other. The universe dilutes away. And when you turn that into a calculation, there's a surprising thing that I want to emphasize. The amount of the material left over today depends only on a cross-section. You would naively think that the amount left over today should depend on a cross-section on a mass, but there was a mass which came in terms of when it froze out, and when you go through the mechanics of the expansion, you find out that the mass drops out. And so we just got a prediction for a cross-section. It could have been any number on any scale, and it turns out to be tolerably close to the weak scale of particle physics, which suggests then if there are new particles that have an annihilation cross-section with themselves that's on the weak scale of particle physics, well, if that is true, then they will be left over from the Big Bang. It's something like omega equals 1 today. And then the second part of the story is that they coupled to normal matter. And so that's sort of a generic idea. So they're coupling to normal matter, and they have the weak scale of annihilation. So it's natural to think that the coupling to normal matter proceeded through the same channel and also is at sort of the weak scale of particle physics. And so that's the freeze-out argument. And so we're still working on that freeze-out argument, even as we haven't found yet new particle physics at the weak scale. So how would we detect these things? Here's a halo of dark matter around the Milky Way. And the dynamics are all sort of known from astrophysics. There's about 300 proton masses per liter of these things. In other words, if these things weigh about 100 GeV, which is natural if they're a weakly interacting particle, there's one in a Coke bottle. Everything in the galaxy is gravitationally bound with orbits of 10 to the minus 3c. So if you weigh 100 GeV and you have a beta of 10 to the minus 3, you have a kinetic energy mv squared of 100 GeV times 10 to the minus 6. That's 100 keV. And if you elastically scatter on nuclei that weigh tens of GeV, it's billiard ball scattering. You get that 100 keV energy just translates into keV recoil energy. So it's a very generic idea. And other than the cross sections, sort of what we need to go detect these things is sort of known here. Any uncertainty in the halo is dwarfed by the uncertainty in what we know about the particle physics. An interesting point is they scatter on nuclei. They can scatter on electrons, but it's natural to think that they scatter on nuclei. There's a bigger signal scattering on nuclei. That's what you're going to want to go detect. Here's some typical rates. Unfortunately, the signal is miserable. It's just absolutely miserable. It's a boring, falling exponential spectrum. The exponential part comes from the sort of quasi-Maxwellian, so-called Maxwellian velocity distribution in the galaxy. And it's this thing you're going to have to distinguish from other backgrounds, radioactive backgrounds, that's just a falling exponential. Here's on 3 different elements. It turns out it's favorable to have a big, heavy element because the wavelength, the simple quantum wavelength, Compton wavelength of these particles, the Broglie wavelength of these particles is about the size of a nucleus. Therefore, the interaction is a matrix element which sums over A, and a cross section, which is the matrix element squared, gives us A squared. So you want A being the atomic weight. So you want a big nuclei. So a signal on a mass, an A100 nucleus is 10,000 times bigger than on hydrogen. So you see that play out a little bit here. These are the 3 main targets people have talked about or that are fielded: xenon, germanium, and argon. Independent of these differences, the overall problem is that the event rate is known to be quite low. Less than an event in a month in something that's sadly the size of me, 100 kilograms. So how are you going to find these? The problem is radioactivity in something the size of me or you, well, me, 100 kilograms, is 10,000 times a second you're being struck by radioactivity. And we're asking to see a particle interaction that's a kind of a featureless spectrum at the keV scale, which is down at the lower end of standard detectors, once a month. So you're going to shield against outside backgrounds. You have to go underground or you have muons. A muon itself is a big signal, but muons cause showers, and the showers have neutrons, for instance. And the detector itself and all the shielding has to be incredibly clean from radioactivity. You can go a long ways to reducing that rate to what you need. It's about a 10 to the, depends how you count, but something like a 10 to the 8th or 10 to the 10th reduction simply by the radio purity. But at some point, you just sort of run out of steam that way. Then this comes in. As I mentioned, the signal you want to look for is when a nucleus is struck. When a nucleus is struck, a whole atom kind of moves. Radioactivity, most of it, about sort of 10 to the 6, most radioactivity is things that give electron recoils. In other words, just gamma rays, which knock an electron out of an atom, or beta decays themselves. The neutron component of radioactivity is about a 10 to the minus 6 phenomena. Neutrons interact with nuclei. Of course, gammas and electrons cause electrons to recoil through material. A little bit of history, since we're in California. The very first WIMP search was taking data from a double beta decay experiment, from a California experiment in the Orville Dam, just a germanium detector, and they looked at low energy, and you see some background spectrum. This sort of illustrates the idea. With the log scale here, those exponential curves I showed earlier are just straight lines. And so this data would rule out that line, but allow that line. So this is a higher cross-section particle, and that's a lower cross-section particle. And in fact, immediately we ruled out the simple notion of a neutrino that would be cosmologically at the right scale and have some very high mass, but have standard Dirac neutrino couplings. If the WIMP has different masses, then it changes the kinematics of the recoil, and so green is a light WIMP, blue is a heavy WIMP. And so by seeing how much of these various, by excluding these curves under that data, you produce a plot like this, which is WIMP mass, and the unknown cross-section and everything above the line is excluded. They're more interacting. Okay. A little bit more history. Well, so how small a WIMP do we expect? The freeze-out argument said that these things are at the weak scale. And if we go back to when CDMS first turned on in 1999, this was the first limit. It's this blue line here. This is some 15 years after the earliest papers sort of exploring the field. And one way to look at it is that the limits, this is in centimeter squared cross-section equivalent on a nucleon, had come down about almost 2 orders of magnitude in that time. We were very excited, and indeed that was a big advance. And people were looking at the time models that predicted, now people would, supersymmetry provides a very natural mechanism for why you would have these particles. So these are various supersymmetric models. Some theorists threw some cold water on this first result. I remember it very clearly. This paper from 1990 or 2000. Here was the result we'd come out with, and they showed some contours down here, sort of. And this is, remember, 15 years to go, about an order of magnitude and a half, and here they are showing many, many orders of magnitude. And they said our results fall considerably below many of the possible predictions in the literature and may discourage some faint-hearted experimentalists. And we should not want our experimental colleagues to be too downcast by the road they appear to have to cover in order to probe our models. And I remember myself being very upset with that. But at the time, people were talking about using liquid xenon. This kind of came out of the work initially with Icarus, Dave Klein's group down at UCLA, and people in England. We're thinking about, well, what about a large detector with liquid noble elements? And in fact, I first made this transparency in around 2002, and 10 tons of xenon would seem like a pipe dream, and it's about there. And it does cover most of this space. So, fast forward to today, and I'm part of a collaboration, the Lux collaboration that has fielded this detector. It's a 2-phase time projection chamber. Particle hits, you get a flash of light. This is a vat of liquefied xenon. Could be argon, could be krypton, but krypton's radioactive, so you wouldn't do that. Electrons also are liberated. There's fields. Electrons are pulled out. They are pulled out of the liquid into the gas, and in the gas they're made to induce a second flash of light, which is bigger. That flash of light is localized with an array of PMTs, so you know in XY where it was, and the drift time gives you the depth. That's the classic notion of a TPC. Here's a cartoon of that. And it works. You've done 3D imaging in a unified liquid, and once you're talking liquid, you can talk about something which can scale. And indeed, this is the current most sensitive dark matter experiment over most WIMP masses. LUX, the Large Underground Xenon Experiment, 300 kilograms of xenon inside of this sort of Teflon box, if you will, and you're seeing an array of photomultiplier tubes which do this imaging. And in fact, there are grids in there that you're looking through. They're deliberately very, very transparent to get good light collection. If you can measure the three-dimensional position of an event, that's very powerful because backgrounds, we can purify the heck out of the xenon, but ultimately external materials are hard, are hard. Any one material is hard. This way we can focus on purifying the xenon alone and having the other materials tolerably radiopure. The radioactive backgrounds will be at the edges of the detector and you can recognize it. Final comment is there's a method looking at the amount of charge and light that we distinguish electron recoils from nuclear recoils. So that's the common background from the weaker, there are backgrounds of nuclear recoils, those are less common, and that's where your signal is. And I'll have more to say about that. This is the set of folks. You see we're somewhere up in the mountains where it's snowing. The reason we're up in the mountains where it's snowing is because we need to get underground. And actually, this is sort of amusing. The place we are is the cavern where Ray Davis first measured solar neutrinos, which is it was just sort of fun. So there's a cavern there. He had the 600-ton tank of dry cleaning fluid and measured solar neutrinos. They finally put a water shield in, and he took a swim. And this has been now turned into a facility, the Sanford Underground Research Facility. And Lux is over in this corner in the Ray Davis's original cavern. And this facility is indeed where the beam, where the planned LB&E and LB&F, LB&E experiment with the beamline from Fermilab is going to go. It's sort of an interesting part of the world. The Sturgis Motorcycle Rally is nearby. This is Lux inside. This is the Lux experiment viewed from the photo before was inside of this. This is a vessel made of titanium, which turns out to be extremely clean from a radioactivity point of view. You see a structure which is trying its best to be as far away from this low radioactivity environment as possible because it's made of stainless steel, which is not so which is a little bit more radioactive. And then there's some 3 meters of water. Water is kind of a poor man's shield compared to lead, but it's a lot easier to manage on a large scale than a lot of lead. So this is kind of a modern way of doing shielding, borrowed from the actually the solar neutrino community, and the neutrino physics in general. So water shielding ranges out gamma rays and neutrons, and indeed spallation, the shower that comes from nearby muons in the rock, and then we're only left with the radioactivity that comes with all these components. Just a quick view of how that plays out. Here are gamma rays going a meter in water and a meter in xenon, which is a much denser material. And I'm just running a movie where I've simulated a bunch. It's hard to stop gamma rays. You can kind of get them angry and they go bouncing around. So you just need a lot of material to stop them. This is the highest energy gamma rays from radioactivity and sort of getting closer to the 10 keV range for WIMPs. Xenon just stops these things dead, but xenon is too expensive to imagine building shielding itself out of xenon. Now, having reduced the external radioactivity, we have to be careful not to have radioactivity in the xenon itself. And so one of the nice things about a noble element is that it's readily purifiable using a commercial device, it's a getter, a reactive hot metal, and you pass the gas over it. All other gases are taken away. You do that before the gas goes down and is liquefied. But that won't work for any other noble elements, and both krypton and argon weakly, are radioactive. So krypton is a difficult background because there's krypton in the air, comes from nuclear fuel, and it's a byproduct of that. And we can't shield it, and we can't remove it easily. We developed a chromatographic system. We could distill it. Chromatographic processes are where you pass sort of a multi-component fluid, be it gas or liquid, through a bed. In this case, it's a charcoal column, and a more volatile, if you will, component goes through faster. So this is the time to pass through this charcoal column, a xenon stream with krypton in it in a helium carrier, and krypton comes out quickly. This is in minutes, and then xenon later, and you get very good separation. And we developed a system, and we removed, in 400 kilograms xenon, we reduced the xenon from 130 parts per billion down to 20, below 20. We got to actually 4 parts per trillion, and that's the sort of scales we're talking about. So the xenon in Lux has no sort of oxygen, water, nitrogen style impurities at the sort of tens of parts per trillion level, and it has krypton removed, and that was done with a getter, down to the few parts per trillion level. And at that point, this background is subdominant. So what does our data look like? This is calibration of our background and these are calibration data. Complicated, the vertical axis is essentially a measure of charge divided by light, and the horizontal is a proxy for energy. And this is electron recoils, and that's the main background from gamma rays in the experiment. They still, at some level, penetrate into our xenon. In fact, this calibration is the sort of the best calibration that's been done of the several experiments of our sort which have run. The reason it's the best is because it was difficult. We actually put radioactive tritium in our experiment. Tritium is long-lived radioisotope. We were one of the few experiments ever to put a long-lived isotope right into the heart of our detector. We had some real confidence in our purification technology. Tritium, it was in the form of tritiated methane, which you can just buy, and the getter removes tritium, and we doped it with an amount which, if we hadn't been able to remove it, we would have had to spend 6 months disassembling and cleaning the detector. But indeed, we removed it in about 7 days. And so that's the main background we expect. If we use a neutron source, we can map out where the WIMPs will lie. They're this population, which in this red area, the center of which you see there, or contrary-wise, this main background up above, its centroid is here. These are two overlapping distributions. And a simple way of thinking about it, below the midpoint of the nuclear recoils, there's very little leakage from electron recoils. And that gives us an ability to distinguish signal from background. It's key. If nature cooperates and the WIMPs are around the corner and we see them in this class of technology, what we're going to have seen, strictly speaking, is a set of particles which were interacting in nuclei, which we'll have to prove, but that should be relatively easy. They were not neutrons. It's a new particle interacting with nuclei in our detector. And so you needed to have distinguished those two classes of events. Just to get a sense of what the data looks like, this is the time. There's the first flash of light. This is just 2 PMTs, each seeing 1 photon. And this is right at our threshold. So this is a carefully selected event. And this is the second flash of light, which is from the charge, which came out later. And see, the time difference gave us the depth of the event. Here's our final WIMP data set. You see this sort of clean area where there's no contamination of the nuclear recoil band from electron recoil band. Of course, we didn't just do a simple cut and count. We did a likelihood analysis of all of this, and here's where we ended up. So, as you probably know, there have been a set of claims of potential discoveries in the past. They are up here, but these relatively high cross-sections and fairly low WIMP masses. And these are the previous limits from experiments. Here's CDMS2, here's Xenon 100, and the Lux result is down here. We're projecting from data we're taking now that we're going to get some factor of a few further. Where does that take us? This is, again, kind of the history of the field, 1985 till, the slide's a bit old, but essentially today. Set of experiments, then with germanium at 77 Kelvin, then the cryogenic experiments, then xenon-based experiments, and here's Lux. And our second result is expected about there. So now let me talk a little bit about the future. So the next experiment is LZ. It's Lux is combined with the previous UK ZEPLIN experiment. We were recently selected in the G2 downselect process, LZ, and Super CDMS to go forward. This is LZ. It looks a lot like Lux. Instead of the 300 kilograms of xenon, it's going to have 7 tons of xenon in the fully active area, another 3 tons kind of around the edges. And we also are doing something better in terms of shielding. We're going to have liquid scintillator completely enclosing this inner vessel. And there's a skin of xenon that's sort of unavoidable in terms of construction. It's only 4 or 5 centimeters thick, but it has several tons of xenon in it, and we're going to read that out. And the combination of those two means that the radioactivity, which the still dominant, the radioactivity from all the parts around the xenon in here has a very high probability of being tagged either inside or outside. Radioactivity is created at the MEV level. For radioactivity to give you a KEV signal in the detector, it's going in, scattering, and coming out. And so by making a hermetic enclosure, a nearly hermetic enclosure outside, you do a very powerful job of recognizing any radioactive backgrounds. How that plays out a little bit is this is a map of the backgrounds we project sort of in a raw sense. And then if we turn on the vetoes, so the external backgrounds you see here around the perimeter of the detector, we turn on the vetoes that those backgrounds go substantially down, and we almost double the fiducial mass. Now what's interesting about this is that we project that LZ in what we're calling the fiducial mass, sort of our definition of the fiducial mass is a little interesting. It's essentially that we're going to be looking only at neutrinos, or hopefully only at weakly interacting particles, neutrinos, and some WIMPs, okay? So sort of inside of this region, the dominant interactions are two flavors of neutrinos. One is solar neutrinos. This is the solar neutrinos. This is the spectrum of neutrinos from the sun. If you followed at all the solar neutrino saga, say 20 years ago, which led to the discovery of neutrino mass and mixing, this is what people were using to study. And what's interesting about it is that, frankly, most of the data came from way out here. This is 10 MeV of energy, and this is flux. This is log scale. So there's these fairly faint burning reactions in the sun, whereas the main reaction that powers the sun are these neutrinos down at low energy, which were partly measured in the chemical experiments, which integrated. They did not distinguish which energy signal they had. So there's this PP burning reaction portion of the solar neutrino spectrum, which in the early 2000s, in fact, there were workshops about can we build a detector to go measure that. If you really wanted to measure it and do neutrino physics, you'd sort of need 10 tons with a clean signal of this. We're going to have 7 tons where this is the dominant five and change tons, where in a narrow energy range, the WIMP range, this is the dominant background. If we actually got the double beta decay isotope of xenon isotopically removed, we would actually do a very nice measurement of these neutrinos. And at that scale, you actually can sort of weigh in and help tickle out. It's important for neutrino for the solar burning modeling, and also you can test various sterile neutrino and other exotic neutrino mechanisms if you do that. On the other hand, those backgrounds are electron recoils. They're the light. They're just the blue color here. It's everywhere, and but it's an electron recoil, and we reject it at about 100 to 1 level. There's another background which, in fact, was recognized a few years ago, which is a little more disturbing, and many of you probably heard of this. Astrophysical neutrinos that are very high in energy, say 100 MeV, can scatter on nuclei through the same process as the WIMPs. So this is just an elastic scattering on the nucleus. There's the A squared dependence, et cetera, et cetera. The kinematics are such that these things, since this is a effectively massless relativistic particle on the heavy nucleus, tens to 100 MeV neutrinos give a signal right in the KeV range where we expect to see WIMPs. And so Strigari, actually while he was at SLAC, and published this paper where we see neutrinos versus energy. A typical WIMP spectrum looks a lot like either of those lines. This is from atmospheric neutrinos, and there's an interesting component, which is the cosmological background of all supernovae. Unfortunately, a little bit indistinguishable from that. This is a log scale in energy, right? And our detectors live in linear scale, where that's about threshold for our detectors, and that's sort of outside their useful range. Sadly, though, these two neutrinos look very much like WIMPs, and as far as people can tell, this is going to be a fundamental background for moving forward. And these are nuclear recoils, so at an event level, they're indistinguishable from WIMPs. Conceivably, in a directional detector, at the 100-ton scale, you would start to get around this background, but that's quite a bit to ask. Where does LZ expect to end up? So here again is the standard plot. Here's the current lux limits, our 300-day projection, and here's what we're expecting. And here's a measure of where that coherent neutrino, atmospheric neutrino background will be. You see it's, yeah, let me leave it at that for the moment. So what we expect then is to jump from here down almost 3 orders of magnitude to there, okay? And LZ is sort of, has been approved and is sort of moving into the CD process. A couple final slides. Work that's happening here at SLAC. So we're setting up, the group that Dan Akrib and I had at Case Western, we were one of the founding groups of Lux. And we and our team recently moved to SLAC, and we're setting up a liquid noble test platform. Here's the tie-in to Steve, that in the former hall, IR2, where the Babar experiment was, and in fact, the hall where the first TPC ran, the so-called TPC experiment, the TPC for Dave Nygren at LBL, we're going to be arguing over space. So here's the LSST camera integration clean room. It's a very large structure, and here we are. This is the old counting hut from Babar, and we're putting in a platform with a cryogenic thermosiphon system that has 24 thermosiphon ports. We can run an array of cryogenic apparatus that will look for liquid argon and for liquid xenon. For LZ, there's a number of project goals. We have a very ambitious, people have not done well who know the details of our field, getting high voltages in our detectors, and that's the primary purpose of all this work, but also we'll test other things. There's other applications as well. I'll mention one is that there's this interesting idea for a next generation of Fermi-like instrument, Fermi-Lat type instrument using liquid argon. And we're exploring whether we can use this test platform to do basic R&D there. It certainly is, the work we're doing with high voltage especially is very similar to what Nexo is facing for double beta decay. And LBNE type argon work could happen here. Let me mention one last thing, since the teaser title of my slide was Towards the Neutrino Floor. If I go back 2 slides, I had us with a limit that was right there, and you see this neutrino floor, which looks just a little further away. Should be careful with that. This little further away is, this curve is well studied. I mean, statistical properties, et cetera. These are the various expected outcomes from the experiment if everything behaves as it is. That's not the limit set by this neutrino background. That's sort of where you're starting to see one event. And you're going to move some distance into it. And obviously, given the importance of of dark matter, whatever we think about supersymmetry, and here's sort of remaining supersymmetry predictions for dark matter, it behooves us to look as hard as we can down as deep into this floor as we can. And the question is, what technology can do that? Can any technologies do that? I have a little bit to say about this in a minute. Let's look out here. This is what we project with LZ, and this limit here is actually kind of 2 things. One is the detector would need to be bigger to go substantially further. 2 is, based on what we know now about the discrimination ability of the detectors, this is also where we're starting to be limited by leakage from the PP neutrinos, which are an electron recoil, and we can only discriminate to a certain level. So coming back to this discrimination plot, this band in LZ will be purely populated with solar neutrinos, some leakage of it. There's some 300 events expected in a 3-year data set, and the leakage is a couple into the lower half of this band, and that results in our limit. So can we do better in terms of this discrimination? It's kind of remarkable that these two bands, they could have been just a little bit further apart, or that band could have been a little bit narrower, and we simply wouldn't have a nuisance background. So we really would like to understand that. I'm going to flash some transparencies here at the end, which are sort of busy, and you're supposed to be impressed by that there's a lot of stuff going on. This is the production of the charge and light signal from an electron striking a xenon, and there's this process where you can either get ionization or direct excitation, which leads to light, or recombination, which comes back. And for electron, and you could also have lost energy directly to heat. And these purple arrows, if I look at nuclear recoils versus electron recoils, you see those arrows are all changing size. And the difference between good discrimination and bad discrimination is the size of these arrows, and also did you screw anything up between when an electron was created and when you measured it, and how well did you do at measuring the light. And the fact is we don't really know whether or not we can eke out. We only need another factor of 10 or so in discrimination in the xenon technology. And if you look at what people have said in the published literature, there is at very high electric field a result that had the required discrimination. Claims that sort of in the conference proceedings realm, the amount of discrimination at lower electric fields varies by about 2 orders of magnitude. So there's frankly just confusion. And my time is up. We're starting to get a handle on it. Complicated. This is the sort of thing that we're mapping out now in Lux, but would be an ideal thing to map out in this test facility. If we can do that, then on this side, with another factor of 10, a next generation experiment could, and you see here that this is the snow mass plot. Here the neutrino floor actually appears about a factor of 10 lower, simply because of how you defined what you wanted to write down. Somewhere down here really is truly the floor. If the WIMPs hopefully are between where Lux is and where LZ will be, if they're not, we really like to push down to there. On the other hand, if the WIMPs are light, and especially if we start to be less motivated, say, by supersymmetry, then we just want to cover as much space as possible. We want to push here, we want to push here, and another talk, which the super CDMS folks could tell you about, is how they're going to push in this direction and that way. Here's super CDMS, and maybe in some super squared CDMS, you would reach the neutrino floor over on this side. Okay, thank you.
Time for a question or two? Giorgio?
Your chromatography slide at the very beginning.
Yeah.
I'm interested in chromatography in general. There's a funny brief on the krypton viscosity. There's a strange thing. If you go back there.
It's a little blip. That's right.
I think I remember it, but let me look at it before I talk.
There.
That's a glitch when the sampling was changed from one mode to another.
Oh, so that's an instrumental.
It's an instrumental effect. Yeah. Although, at the scale of those sorts of things, that's the sort of thing we have to chase down to change 4 ppt into 0.01 ppt, which is what we need for LZ, and that's ongoing R&D work. In that particular case, I'll probably get in an argument with our grad student right in front of you if I try to address this.
Neutrons that were a source of background, and I thought that was a big factor in CDMS. So how do you suppress those substantially here?
Yeah, that's a good question. The quick answer, well, so if you go deeper, of course, you suppress it. Homestake is not in the class of the deepest sites. On the other hand, once you switch to water shielding versus lead shielding, you get a big improvement. 2 reasons. One is, thick water does, well, first off, we can have quite a bit of shielding cheaply once you've paid for the cavern, okay? And so in this case, that's taken care of. And the second thing is that you really get in trouble with neutrons generated by muons when you have a lot of heavy materials nearby the detector. Water is not good at converting muons into neutrons, And so by having a water shield, we sort of are okay. Okay? So there was a lot of studies at the early time we were doing all this. Where would that muon-induced neutron background end up? And the answer is that probably even at Gran Sasso, where the muon flux is about 20 or so times higher, this type of technology is thought to be good enough for quite some distance down.
All right.
Expectation of the limits they can reach and, and the place they have in all this.
I think I grabbed the plot. Well, oops, one more, sorry. So dark, well this was everyone's aspirations prior to down select, and down select means that the majority of these are gone. They're not funded. Deep 3600, which is going to turn on, is there. So I think a way to look at it is that argon, the problem with argon, of course, is it's radioactive itself. It's this remarkable story. It's quite radioactive on this scale and also has quite remarkably good discrimination based on the pull shape alone. The problem is that that is very energy dependent and it's very poor low energy. And so exactly where the threshold ends up gives you, you have an exponential falling rate, and if you have a high threshold, then you've really lost signal. And so a 3.6 ton argon experiment is, it's this curve, is a slightly better in projection than Lux with 300 kilograms. So essentially argon spots xenon a factor of 10 in mass is one way to put it. And that's if they actually demonstrate this threshold. We'll see where that turns out. I think they probably will. So I think at the end of the day, argon is about a factor of 10 per mass worse than xenon. And essentially based on that, the larger, the argon experiments in the USG2 process didn't advance.
And let's give Steve the last question here.
I missed your sense about the reality of this 10 times better discrimination at high electric field. You said something's been measured, but you cast some. Who's measured that improved discrimination?
The ZEPLIN side of LZ. The ZEPLIN 3 experiment had 99.99, 10,000 to 1-ish discrimination, whereas LZ is predicated on 200 to 1 discrimination.
And what's the difference in the bias that they're using?
So that detector was first off, it was small scale, it's fairly short. They had an electric field which in LZ would require putting 600 or 700 kilovolts into the experiment. Now, personally, I think that it's likely we're going to find that the answer is somewhere between for a moderate field, but to get an extra factor of 10 in xenon is going to require significant work on the electric field and also a mastery of all the factors that could spoil your other bits of it. And I think there's some reason for optimism, guarded optimism, that it may be there, but we simply don't know.
Okay, let's thank Tom once again. And then is Adrian Lee from UC Berkeley setting up here. He's going to tell us about gravitational lensing and the search for inflation in the cosmic microwave background. And I'll give you a warning at 2 minutes.
but I have to put this in here for that, right? Yeah, it's okay. Yeah, that's fine. Okay, thanks. Okay, thank you very much for inviting me here to give a talk at this very nice occasion of KahnFest. I'll be speaking today about gravitational lensing and the search for inflation in a cosmic microwave background. And this is a very exciting field right now, and I hope to give you some sense of that. Here's an outline of my talk. First, I'm going to introduce the science. I'll talk about inflation, which may be putting the bang in the Big Bang. And then I'll go on to talk about gravitational lensing of the CMB, which promises to teach us a lot about large-scale structure. As an example, I'll talk about the experiment that I'm working on called the polar bear experiment. I'll talk about the development of the experiment and our first cosmology results. No CMB talk would be complete these days without mentioning BICEP 2, and I will address press releases and internet leaks from today, very briefly. Finally, I'll talk about the future of the field. So since I'm here at Stanford, I really don't have to introduce inflation, but in case there are any new students in the field, I'll be very brief and introduce it. So if you take the very simplest Big Bang model, just that you take the current expansion of the universe and run the movie backwards, you will realize that that model doesn't work for explaining the most obvious features of our universe, that we observe the universe as homogeneous, apparently one temperature, geometry is very close to flat, magnetic monopole density is low, and so we need a new idea. And inflation is a beautiful and very simple idea. You can write it down in one line here. It's an exponential expansion of space, and that one simple idea solves these problems and creates a flat, homogeneous universe. And the other exciting thing that's going on now is that evidence is building for inflation as we make more and more cosmological observations. Here's a cartoon of how inflation works. Scale factor, and look at, observe the exponents on here to get a scale, minus 60 to 40. And same thing in time, very large dynamic range here. And here's the theory that if you put in a very brief period of exponential expansion, everything moves outside the horizon, and what you're left with is a locally flat, homogeneous universe. Now, it's a very simple idea, but what would drive that? What would be the physics that would drive that exponential expansion? Well, the ideas, the vocabulary and the ideas are all borrowed from high-energy physics. You have people talk about a vacuum energy density. Where do you get this thing? Well, you can appeal to scalar fields. For example, the Higgs, those even ideas early on that the Higgs might be the inflaton. These fields would be at very high energy, gut energy scales. And recently, thanks to people like Ava, we have possible successes in having inflation being driven in string theory. Now, I've spoken a lot about inflation, but are there alternatives? I would say we haven't proven that inflation occurred yet. That's one of the things we're looking for in the cosmic microwave background. And as you all know, there are cyclic universe theories, and at current data, people can try very hard and try to make those theories work with the observations. Okay. Here's a cartoon that you've all seen of the history of the universe. Perhaps you didn't know that the inflationary period was a little bit orange, a little bit white, and mottled. So very early on here in the universe, at a fraction of a second, you have this exponential expansion. Then the universe expands and cools, and when it cools to several thousand Kelvin, where neutral hydrogen can form, the photons that were bouncing around with the hydrogen plasma, like pinballs in a pinball machine, are free to have a mean free path of order the entire size of the universe, and they stream all the way to our telescopes unscattered, and we can, by looking at those, we can make a map of the universe essentially at this very early time at the beginning of the universe. After the CMB is released, then the photons and the matter, they part ways, and the matter goes on to form the first stars, the first galaxies, and larger structures as time goes on. oops, let's see. Oh, and so getting to the theme of one of the themes of the talk, if inflation occurred, it acted as a gravitational wave antenna, but in transmission. And it would make gravitational waves that would hang around like a gas. And as the universe goes neutral, it would give a small polarization to the CMB photons. And importantly, it would give it a polarization with a pattern that has a handedness, these so-called B modes. And the standard scalar, the density perturbations, should not give you these B modes. And so looking for these B modes is the search that we have to do to look for the signature of inflation. So here's what we look for more literally. Here's a power spectrum, microkelvin in the y-axis, an angular scale. Here I put, this is multipoles, so the angular size is getting smaller this way, and I put some numbers here to orient you, 10 degrees, 1 degree, 0.1 degrees. This is the first acoustic peak that the field worked so hard to find and shows that the universe is very close to flat. But that's a relatively big signal compared to what we're hunting these days. You come down here to several microkelvin, and you see the E modes. And then you come down further. Now we're talking about several hundred nanokelvin, and we see the gravitational lensing. So that's the E modes being lensed by large-scale structure. And some of those E modes are converted to B modes, and so we can see them here with this characteristic shape. Now, I showed the inflationary signal here, which is also B mode, but I showed it as a range because we don't know this amplitude. This amplitude tells you the energy scale of inflation, and so we have to dig down to look for this signal. Here are our current constraints, largely driven by Planck temperature data. Here's the so-called tensor to scalar ratio, tensors being the gravitational wave, scalars being the normal density perturbations. And so the higher the energy of the inflation, you go up in this direction. This is the primordial tilt. This is the exponent of the power law of the primordial spectrum. Basically, is it white noise or does it have a slight tilt? Inflation theory predicts that it has a very slight tilt, just a little bit off of 1. And so you see that, first thing you see is that current data does suggest that the tilt is a little bit less than 1. And in fact, this is now becoming 5 sigma and beyond significant. So as I said at the beginning, there's growing evidence for inflation, and here's one. This was a prediction of inflation theory, and it's being borne out. In terms of the tensor to scalar ratio, you will see you can look for that in the temperature anisotropy at small multipoles, and right now that's sitting an upper limit of about in this 0.1 range. And I'll come back to polarization and what we're learning from that. Okay. So people like to say that the early universe is equal to a high energy laboratory, and that's of course because as you go back in time, the energy scales get a lot higher and higher, and if we get to inflationary scales, we're getting to this 10 to the 16 GeV, so this gut energy scale. So at least the energy scale is much higher than LHC, and so if we can measure this signal from inflation, it's very promising for exploring this high energy physics regime. And in fact, for me, one of the most exciting things about this search is not just proving if inflation is correct, but all the things that we haven't predicted yet from this signal. As I said, we'd be working these ultra-high energy scales, 10 to the 12 higher than LHC right now. And allow me to be a little bit speculative here. If you saw structure in that signal from the early universe, could you possibly see evidence for a multiverse? The signal is intrinsically quantum fluctuations of the metric, the gravitational wave signal. Would we learn some connection to quantum gravity theory from that? There are, as I said, recent successes in creating string theory-driven inflation. Can we learn something about string theory from there, from these measurements? And lastly, but not least, inflation and dark energy both give cosmic acceleration. In fact, you notice that all the language I used, vacuum energy density, scalar particles, that is common between this early exponential expansion and the current one. And so is there some deep connection here? If we measure the signal, will we find something out about that? So now let me speak about gravitational lensing. So here you have the CMB as a backlight from very early in the universe. And as the photons traverse the universe, they get scattered by intervening overdensities of matter. And just like optical weak lensing. And, but a complementarity between CMB lensing and optical weak lensing is that our backlight is very, very early in the universe, so we are essentially sensitive to all the mass in the universe. In other words, we have an integral measure of all the structure all the way back to the time of the CMB, which is essentially all of it. And so you can see that here, that this is the kernel of the lensing, function of redshift, and you can see it peaks up here at several, but it goes all the way out to the time that structure is forming. Okay, now, the nice thing about optical weak lensing is that you can do tomography. You can do 3D measurements and break it up into redshift bins. And so a nice connection to Steve's work is that in the future, optical measurements and CMB measurements will be combined to get the best constraints and to measure large-scale structure. Now, as I said before, in CMB lensing, what's going on is you have these E modes that are made by the primordial density fluctuations. And think of toothpicks on the sky as representing these E modes. Then the lensing just pushes the toothpicks around. And once you can do that, now you can form both E modes and B modes. And in fact, you get both. You get a contamination of E modes and a contamination of B modes from the lensing. And that's a temperature lensing signal. So one of the things you can do with this is to look for the sum of neutrino masses. How do you do that? Well, the neutrinos act as hot dark matter, and the larger fraction of dark matter that's in neutrinos, the more suppression you get of large-scale structure. And so as I dial up, as you see here, the amount of the higher the neutrino masses, we suppress structure, and that's the signature we look for. Now, so I give a motivation for looking for these massive, for the massive neutrinos, and the physics there is really beyond the standard model and pokes at the idea of matter-antimatter asymmetry. The sum of masses has to be above 58 millielectron volts, and future measurements, as I'll argue, are going to be able to get to that level. Okay, so I'll now tell you about Polar Bear. Here's our collaboration that spans 3 continents and many countries. This is a picture from a recent collaboration meeting in UCSD. And here's a picture of our telescope. It's a 3.5 meter off-axis telescope, about 17,000 feet high in the Chilean Andes. This is ALMA over here. And it's an off-axis dish. And we worked very hard to keep the optics very clean so that we don't pick up spurious signals from nearby ground. Here's a photograph of the group assembling the camera up at 17,000 feet. You can see my former student, Ziggy Kermish, wearing an oxygen prong here to keep his IQ as high as possible while working. And here is our detector array, 1,274 TES-based detectors in that focal plane. And I'll be talking more about detectors in a little while. Oh, and here's a little movie, if I can get to run, and just showing scanning on a nice day back and forth and making maps. Now, as I said at the beginning, the signals we're going after now are hundreds of nanokelvin. And if you compare that, for example, to ground structure, which is at hundreds of Kelvin, you need to have you need 2 things. You need extremely sensitive detectors, and you need excellent rejection of systematic errors. There are many effects that can leak spurious signals into your measurement, certainly at the hundreds of nanokelvin level. So first, let me talk about getting the sensitivity. And so this shows you the evolution of detector sensitivity. This is, in the y-axis, this is a measure of mapping speed, basically in Kelvin units, and so lower the better. And this is the year. And you can see that evolution has been very rapid. And this is very much like Moore's law. And in fact, it's faster than Moore's Law. Moore's Law is a doubling every 1.5 years or so, and we've been doubling on average every year. Now, just like computer Moore's Law, that doesn't happen by accident. There's been a lot of hard work, and I'm showing you here arrays that we developed at Berkeley, but this is common to the whole community, and Kent Irwin gave you a talk about this evolution yesterday. First, we started out with Apex SZ early on, about 2003, about 300 detectors here. SPT SZ array, getting to a kilopixel. Polar Bear 1 is also about a kilopixel, but now it's dual polarization. And then I'll talk about a future instrument. Polar Bear 2 has about 8,000 detectors and now having multiple colors per pixel. So that's another trick we can pull in trying to stay along this Moore's Law-like progression. And here is a photograph of a Polar Bear 2 detector. This scales about 2 millimeters here. And what you're seeing is what's called a sinuous antenna. You see there's 4 arms. And it's called sinuous because the arms sinew back and forth. You can think of it as each little section is a dipole antenna for that particular frequency. So 2 sides makes 1 polarization. And it's many dipoles connected in series. And so it can pick up a very wide range of frequency. In fact, there's no limit intrinsically. It's just given, the bandwidth is given by the ratio of the inner size to the outer size. So then what we do is we pull the RF out with a transmission line. We select frequencies with filters, microstrip filters, and then they end up depositing power near a TES detector. So here we're just splitting it in 2 ways, but we've split it up into as many as 7 ways with our technology. And this just shows that we put this behind a lens slit about 6 millimeters across, focuses light onto the antenna. And here's our facility at Berkeley. 3 years ago, we got a new facility, several thousand square feet, and that's been working really well for us. That's a picture of me and some former students. And so one nice thing in our lab is that the students have played a really big role in the detector development and fabrication. So here, next I'll talk about our results. Here's a B-mode power spectrum as of 2014, so pretty recently. And you can see here, again, is the theory of lensing, theory of inflation, and you see all these upper limits. Now, of course, these upper limits represent a lot of very hard work by the community working on these experiments. But if you want to see these signals, you need a big jump. You need a big jump in that Moore's Law progression. So what we've done is with Polar Bear, with the kilopixel array, we've taken, I'll be talking about just our first year of data, and we made a very deep map. This map is about 3 degrees by 3 degrees, so we went for a narrow piece, but very deep, and this is 10 times deeper than Planck, roughly. And so this is getting to this hundreds of nanokelvin ability. And these are the most sensitive polarization maps existing at small angular scales, similar to the BICEP maps at larger scales. And that's quantitatively the number. Okay. Now, as I said, lensing produces E and B modes from E modes. I talked about how you can move the toothpicks around, and so this cartoon shows that. And then taken together, you can measure the deflection field, basically the direction in which the photons were deflected by intervening structure. And that allows us to make a map of that deflection field. Now, whenever you read, for people outside the field, reading our lensing papers, it looks like an alphabet soup. E's, B's, EB, EB, all these things. What's it all about? We have many ways of quantitatively measuring lensing. One thing we can do is we can cross-correlate the density, the deflection with galaxy density being another large-scale structure indicator. And that was first done by SPT in a very nice paper, Hansen et al. In 2013, finding B modes correlated with large-scale structure. We followed it up with our own measurement in 2014. But you can also now, of course, measure it with CMB alone. And measuring the deflection spectrum directly, which gives you the best cosmology constraints. That's the way to get at all the things that I was discussing earlier. And finally, you can measure it directly by measuring the auto spectrum of the B modes in the maps. Okay? And I will talk about our measurements of all 3 of these. Here's our polarization deflection spectrum measurement, and this is CSABEL. versus L. And here's our data. And this represents a 4.2 sigma detection. Here you can see simulations and showing that this would be above, well above 0, confidently above 0. And this is represents the first measurement of B mode lensing using CMB data alone. Okay. Now I'll talk about our auto spectrum. For that, I'll come back to here because these are auto spectrum measurements. And so I remind you that we need a big jump. And here's our measurement of the auto spectrum of BB. And this is on small angular scales. Remember, we measured very small patch, so we can only measure relatively small scales so far. And our angular resolution, though, allows us to get at this peak. And so we've been able to come down the needed jump and measure this BB auto spectrum of lensing. And I'm showing this in right order in temporally because this was a very exciting week for B mode CMB. We released our results on Monday, and I think it was Friday that BICEP 2 came out. So 1 week later, you went from nothing to having both of these measurements that connect up very nicely. Now, so here are the results. You've seen them many times. And so one of the things about these measurements is that they really represent a new generation. The ability to measure hundreds of nanokelvin and measure them both with the sensitivity and systematic error cleanliness is really a big leap. So this is going to allow us to start to really get at this science. Okay, so I said I would discuss the things that are happening right now, and you know this plot. This is the power spectrum amplitude versus multipole. And it's a paper that Planck put out now many months ago. And what it's showing is here's a theoretical spectrum for R of 0.2, and that was the initial report from BICEP 2. But then the blue boxes are dust measured by Planck at 353 gigahertz, extrapolated down to 150 gigahertz on the BICEP 2 field, and then measured as a power. And you can see the very interesting thing is that it's consistent with the theory of an R of 0.2. So I'm not going to show plots that are appearing on the internet. At least I think they were put on, they weren't taken off. Okay. So I won't show those, but for people who've seen them, it's consistent with this. And what's new is the data were combined. The Planck data and the BICEP 2 data and the Keck data were combined to estimate R. And a one-liner is it appears consistent with an upper limit of R of about 0.1. And certainly doesn't rule out a signal there, and you have to look at the details. But if I had to give it in one line, that's the way you would summarize it. Okay, so you can ask me in questions we can talk about it more. Briefly on systematic error control, as I said, there are leakages that can give you spurious signals. If you're differencing two beams to get at polarization, usually in most of the instruments we're working with, and so if the beams aren't identical, you will leak a little bit of temperature to polarization because you will think that your temperature signal is actually a polarization signal. So if your beams are different sized, they're pointed in different places, they have different ellipticities, or the gain's different, you'll get beams like this leaking temperature to polarization. And as I said, this is one of the big challenges for getting to this 200 nanokelvin level from the hundreds of microkelvin of temperature and isotropy. And so what we've done with Polar Bear is we measured our instrumental parameters, fed those into end-to-end simulations, and then measured how much leakage we would expect. And so the important thing here is here's the theoretical expected signal, just simulated, and here is the sum of our systematic errors using our measured instrument parameters. And I won't get into all the details of these, but they're all the various leakages. But the important point is they're well below our measured signal size. So we have a very clean measurement of that lensing. And they get, with our small beam, these systematic errors only get better as you go to L of 100. So as our experiment can get to lower L with larger patches, many of these will get lower at low L. And so that promises to help us make a nice measurement down there. Okay. Let me go on to tell you about the future of Polar Bear. We're making the Polar Bear 2 receiver, which, as I said, has about 8,000 detectors. Each pixel has 2 bands, 2 polarizations, so 4 detectors, and that's going in the back of a much larger receiver. There it is being assembled at KIPAC in Japan. This is a courtesy Photoshop. Here's our existing telescope, and here are the ones under construction, and these are under contract, and they're deploying in less than a year. So we'll have 3, the Simons array refers to the fact that we'll have 3 telescopes to get to higher sensitivity. So total, it'll be at 23,000 detectors, resolutions 4 arc minutes to measure lensing, as I argued, it has a systematic error advantage in leakages. We'll have 2 to 3 bands per pixel, but we've done up to 7. So since dust is obviously so important, our multi-chroic technology is well placed to explore that. Scalability, we'd like to expand that in the future. That's one of the important things. We could go to more telescopes and larger arrays. And as I just said, this is very timely because we need both high sensitivity and more bands to decipher the signal underneath the dust. And once detected, if we detect it, Simon's array can narrow toward one inflation model. And so here are the constraints that we'll be able to set with Simon's array. And the bottom line is that if R is bigger than 0.01, we'll be able to make a sensitive measurement. Okay. Here are the constraints on neutrino mass. An important thing is it's very complementary to galaxy density measurements. I use, for this example, DESI. And in this plane of omega mh squared versus sum of neutrino masses, almost 90-degree degeneracy breaking here, with giving us very tight constraints. And we may be able to measure the minimum at several sigma. Okay. Oops. I actually, not that. I do want to say that, but that. Okay, I'll come back to that. I only have a few slides left. The future, the scalability is important because we're looking at expanding, and this is the community as a whole in the US, CMBS4, which is a so-called stage 4 CMB experiment. Here's a white paper that John Karlstrom and I played a role in. And the idea here is it sounds a lot like the Simons array, multiple telescopes, 3 arc minute resolution, and multiple sites. Final topic is the Lightbird experiment. And this is a space proposal and initiated by Masashi Hazumi in Japan. But just recently in December, we submitted a NASA mission of opportunity proposal to build the detector arrays for the Japanese mission. And this is going to be a collaboration between Berkeley, Stanford, so that's Kent and Shaolin, NIST, Colorado, and San Diego. And so it's a very nice opportunity to have a Bay Area collaboration on the detectors for Lightbird. This cast of characters and across many continents, yet again, a CAD drawing of what the instrument would look like. And so briefly, it's 2 telescopes, one that's about 0.5 meter, and that's a low-frequency telescope, goes to about 260 gigahertz. Then there's a high-frequency telescope that goes all the way to 400 gigahertz. And these detectors will be the scalar horn detectors that Kent Irwin has done so much to develop, and these will be the sinuous detectors, taking advantage of their complementary strengths. Oh, and I have pictures of them. So that's the sinuous, and these are the horn-coupled that Kent has been developing. And a close-in on the horn-coupled detector. This is what the bands look like. Now that we know dust is going to be a tough thing to measure very well, we put 15 bands into our measurement, and that's one of the great advantages of space, that no atmosphere to contend with. You can put the bands where you like, and this will have very strong ability from 30 to above 400 gigahertz. So we worked quite hard at forecasting how well we could do against foregrounds. And actually, this is an interesting story that I don't have time for, but the standard analyses look like this, but our analysis for the proposal looked like this. And this has to do with putting in actual Planck data for the foreground simulations on the variation of indices, the spectral indices. But the bottom line is we can get to about half times 10 to the minus 3 in R, including the simulation of foregrounds. So I'll summarize. I talked about polar bear. It's the first measurement of B-mode deflection and the B-mode autospectrum using CMB data alone. And as I tried to emphasize, these measurements require both sensitivity and stringent control systematic errors. The hunt for inflation's on, and I talked about all the great things we're after there, that the early universe means ultra-high energies, that there's a great opportunity for discovering things that we haven't even thought of, and that we really need to constrain foregrounds. In the future of Simon's ray is a unique design for the science, and the idea of combining a 30 arc-minute resolution space mission such as LIGHTBIRD, I didn't say that, but that's what that mirror size gives you, and a high-resolution ground-based experiment, this is a very powerful combination. Thanks very much, and now I have to go back to my slide and congratulate Steve here.
Okay, questions? Hot off the press data? Back?
So when would LIGHTBIRD launch, and would that be a small Japanese satellite, or would that be something larger?
Yes. Okay. So the currently planned date is 2022, so a little less than 10 years from now. And LIGHTBIRD has evolved and has become less light as time has gone on. And so now it's paradoxically classified as a large JAXA mission. Now Spica is beyond that category, but it is large now.
Okay, other questions? Yes, Lance?
Could you show the polar bear BB data again?
Yes.
So there's one point that had a different symbol and no error bars on it.
Yes.
And all the points seem to be a bit high, and I thought SPT was also a little higher than the lensing predictions in that area.
Okay. So several points there. That one different symbol is there because it's negative, and there's no problem with that. It's just as a log scale. So you have no good choice. We talked about this, had long meetings about it. Statistically, this measurement is fine. So we simulated it, of course. And then the second question was about. Yeah. So one thing to be clear about is the first SPT measurement was different in that it was cross galaxy, and so you even though people were plotting it on BB, technically it's not quite the right thing to do. It's understandable why people do it. There's so much excitement over bicep 2 and all these measurements. You want to communicate that to people, so people put it, but it's not really the right thing to do. It's the inferred BB, what you would get, and to my knowledge, it's statistically fine with the amplitude of lensing, but yeah.
So let me ask the question with what's hot off the press. What's the sigma associated with the noise? So you said 0.1 is allowed, and
Yes.
what's the sigma of the cross correlation?
Okay, so what I saw on the internet before it went away was some probability density curves, and they're in my mind's eye. So I'll draw it for you. There was a plot that went from 0 to about 0.2, and to cartoon the error bars, it looked like this, right? And so, and it depended on whether it was bicep 2 or KEK data. Bicep 2 was somewhat higher, but consistent with KEK. KEK was somewhat lower. KEK was hitting 0 fairly high in the curve, but bicep 2 was hitting in the falling portion. Okay, so need some thought and examination.
Yeah, the paper is going to be put on the bicep KEK site within the next half hour.
Yeah.
So
A half hour, okay.
Yeah.
Okay. Sorry, I should have called you up to talk about this part.
Any other questions? All right, let's thank Adrian once again.